This is a big clue one right here, right? So it's like it's telling you that this is an SN2 reaction. It's proceeding via SN2 mechanism. So we're going to draw the transition state for this particular process and then try to explain why you're having what's called stereochemical inversion. And this is kind of an interesting feature about SN2 reactions. They proceed via stereochemical inversion. So let's talk about that aspect first before we get into the chemistry. So what does this actually mean? Stereochemical inversion. If you start with the reactant that's right here, you'll notice that this is what type of an alkyl halide is this? Leaving groups connected to carbon. How many carbons is that touching? 2. So this is a secondary alkyl halide. So whenever you're dealing with secondary alkyl halides, you have to consider the possibility that there could be some stereochemistry kind of going on in this case. Well, it turns out this is an asymmetric center. So it's a chiral center, and it happens to have an R stereochemistry to it. You can work it out and kind of see where it comes from. But look at what happens in the product. So when the product forms, so the chemistry happens at the electrophilic position right there. But what do you notice here? 1, 2, 3. It looks like it's R, but it's actually really S. And so that's what stereochemical inversion is all about. You're converting from one stereocenter to the other stereocenter. You start off as R, you go to S. Or you start off as S and you go to R. This happens all the time whenever you're dealing with secondary RX, secondary alkyl halide electrophiles. Those are very, very important to know. All right, so let's mark this up really quickly using our color scheme here. So we have a sulfur, which, by the way, sulfur, whenever you see an S minus, a sulfur anion, that is a dead giveaway that this is an SN2 reaction. Anytime you see it, you go, boom, SN2. I tell students that every semester. Maybe about a quarter of them actually listen to me. But that's whenever you see it, that's like, what type of mechanism is this? I see a sulfur. It's probably SN2 right there. It's kind of a cool little trick right there. But this is our electrophilic position. It's touching the leaving group. And remember, the goal is to get what? It's to get the nucleophile to line up. Sorry. Oh, can't draw this right. I want to get that nucleophile to line up with the electrophilic position. And then that also needs to line up with my leaving group, right? So they need to be basically in opposite directions. They need to have sort of like a bond angle of about 180 degrees, right? They got to be more or less linear in this case. All right, so how do we actually show that? Well, this is the tricky part. You have to draw this somehow showing that you have your sulfur, carbon, and bromine all in alignment with each other. So start from that point. I like to draw my nucleophiles on one side, on the left-hand side. Oops. So I might draw my nucleophile kind of coming in from this perspective. I'm going to move the methyl group around to the other side of this. I know my carbon is going to be right there in the middle. And then my leaving group is going to be this thing. And I know there's going to be what we call a dative bond between the nucleophile and electrophilic position and then the electrophilic position and then the leaving group right there. Now I just have to put in all of the remaining atoms that are in this thing, right? So what do we have here? Well, basically what we've got is we have a CH3 that's pointing up in this direction. We may have we have a, what is this, a 2-carbon unit that's sticking out like this. This is CH2, CH3. And then we may have a hydrogen sticking in kind of this direction here. But this is one way to show what the transition state basically looks like. This is, you want to draw a diagram of what your transition state looks like for this particular process. This is it. This is your winner chicken dinner right here.